And in this one instance, I also need to add in another term, just allowing for the possibility that there is sort of what's called an exceptional Landau's equals 0 in this problem. This is not going to be something that's going to make an appearance on any other slide. It's not going to be kind of the main issue for the most of the theorems I'm going to be considering. And instead, what really is kind of the key point is that this theorem is fantastic. And it tells us that we get lots of primes as soon as we're looking at an x that's bigger than discriminant to some large power. So this is fantastic. But a problem arises in that in many of these applications where one wants to use Chebotarev, you want some primes that are a lot smaller than this. You want them to be maybe some very small power of the discriminant or something like that. We'll see these applications in a second, or maybe sort of maybe 10 minutes from now. And in particular, then, this theorem is not actually strong enough to give you something that you can use unconditionally. All right, so what's a workaround? Well, if you're willing to assume GRH, if you assume this kind of for the Dedekind zeta function of the field K, then you get a much, much, much stronger result. In particular, if you assume that x is bigger than just now log discriminant squared, this is some small power of the logarithm of the discriminant, times some log logs, then you get the Chebotarev density theorem being true like this. So you actually get a stronger error term as well, but really kind of, again, the key point here is the range of x allowed. And so this is fantastic. This gives you lots and lots of primes in a really useful range. But of course, there's a problem here, which is that GRH isn't a theorem. So what can you do if you want something that's unconditional, but better than sort of the Lagarias and Odlyzko style effective result from the previous slide? And so here, there's a beautiful idea due to Lillian Pierce, Caroline Turner-Butterbaugh, and Melanie Wood, that if you sort of look at a family of L functions, there are these things called zero density estimates. And essentially what they say is that in this family of L functions, GRH, or something kind of close to GRH, is sort of nearly true for almost all L functions of fields in a family. So the kinds of families I want to be considering are going to be sort of families of number fields with given Galois structure. So just to define that carefully, given a permutation group G, I'm going to let Fg of Q denote sort of exactly the set of extensions K over Q with Galois group G and discriminant bounded by Q. Okay, so this is sort of the family of fields I look at, or that I guess Pierce, Turner, Butterbaugh would look at as well. And in very loose terms, their theorem asserts the following. If you assume the Artin conjecture, you assume the discriminant multiplicity conjecture, okay, for this family, words on that in a second, then the Chebotarev density theorem holds as soon as x is bigger than essentially a very sort of arbitrarily small power of the discriminant for almost all fields in this family. So I'm not going to say very much about the Artin conjecture, because in fact, in 2 slides, I'm going to state kind of a slight improvement over this result due to Jesse Thorner and Asif Zaman that actually removes the Artin conjecture. But the discriminant multiplicity conjecture is going to be a key actor in this talk, or at least sort of in some form. So I do want to kind of spend some time kind of talking about why we see that, why we sort of need some sort of kind of field counting type result here in this sort of work of Pierce, Turner, Butterbaugh, and Wood. So from my perspective, okay, the reason for needing some sort of field counting technology is the theorem of Aramata and Brouwer, which sort of implies that if you have a subfield of your normal sort of extension K, then zeros of the Dedekind zeta function of this subfield F kind of propagate up into sort of this Dedekind zeta function of your normal extension K. Okay, and just saying, so subfields can occur for many different fields in your family. You sort of can see exactly the same subfield that can arise sort of for many different fields in your family. And these things are just going to correspond to normal subgroups of your Galois group G. So if your group G has some interesting normal subgroups, then there are going to be subfields that sort of arise possibly for many different sort of fields in your family. And kind of corresponding to this Aramata-Brouwer theorem, if you have a bad zero in just one of those subfields, it can propagate to many, many, many fields in your big family. And so kind of to account for this, I want to sort of define what's, or this is a good example, is that if you look at sort of G being Sn and your normal subgroup being An, and this is going to be kind of a main thing we're going to be considering on this talk, is like sort of this kind of family, sort of with G being Sn and N being An, then sort of the subfield corresponding to An is just the quadratic field Q adjoins square root of basically the discriminant of K. And to account for the fact that this one subfield can arise for many different sort of Sn extensions, we're going to define this so-called intersection multiplicity, which basically just sort of says, what is the maximum number of times, sort of as you vary over fields in your family, that you can get some sort of interesting intersection. So that's what this is. And then what this Pierce, Turnage, Butterball, Wood kind of result says, and again, I'm going to sort of state in a slight improvement due to Thorner and Zaman, is that sort of for all but sort of O of Q to the epsilon sort of times this intersection multiplicity fields in your family, you're going to get a very strong Chebotarev density theorem. You sort of have X bigger than some sort of arbitrary, some large power of log discriminant. You're going to get the Chebotarev density theorem you want outside of this kind of exception set. So this is fantastic. You get lots of primes in a really useful range for most K. But that assertion that you get most K sort of assumes that this intersection multiplicity is something we can understand. Okay? We need to assume that this intersection multiplicity is small. So there are two problems that kind of arise now when you look at this theorem. The first is kind of technical, which is that counting fields is a really hard problem. We really are very terrible as a society at understanding sort of the number of fields that have some given Galois structure. And correspondingly, it's going to be even harder to understand sort of how these fields intersect. And so just kind of, for example, even sort of counting Sn fields for n greater than or equal to 6 is open. We have no idea how to do that. And correspondingly, we can't actually rule out the possibility that almost every Sn field intersects almost every other Sn field. And so that means sort of it's possible that this MF of Q is actually really, really massive. And it's basically the size of your family. So we don't actually know that this theorem necessarily applies to sort of these kinds of groups. The other problem is a little bit more structural, and it asserts basically that fields genuinely can intersect. If you really do look at Sn fields, they do have quadratic subfields, and you will see multiple Sn fields that have the same quadratic subfield. And so this is kind of baked into this, that this MF of Q genuinely could have some size, even if you sort of believe it should be small in general. So it's these sort of issues that my work with Jesse is hoping to bypass. And so in particular, we're going to bypass the subfield problem by finding some way to sort of get past sort of these issues. But because the subfield problem is structural, we're necessarily going to have to give up some information. In particular, the information we're going to have to give up is the information that subfield we're trying to bypass tells us. Okay, so more specifically, what we're going to try to do is to bypass the subfield corresponding to some normal subgroup of our Galois group G. What we're going to do is we're going to only target equidistribution in fibers of the projection from G to G mod N. So that is, we're going to basically say we have no idea sort of how things are distributed in G mod N, and just try to understand how they're distributed kind of in this relative projection. So put another way, conjugacy classes upstairs in G descend to conjugacy classes downstairs in G mod N. And so for each conjugacy class downstairs, we want to look at sort of the conjugacy classes that map to it and show that they have the right relative density sort of compared to each other. So this is what Jesse and I show. All right. So let N be a normal subgroup of sort of our Galois group G, and let Kn denote the fixed field of N. And then we get an effective Chebotarev density theorem kind of in this sort of fibers world for X that are sort of bigger than this large power of the discriminant. Okay, sort of we get it sort of in this form. Okay, so I know that this sort of main term is going to be a little bit sort of take a little bit of time to process. I'll sort of do that actually on the next slide, I think. But first, kind of the key thing to note is that whatever this Chebotarev problem is, whatever this sort of weird pi c prime is, it's happening in G mod n. I'm sort of shifting the burden of understanding sort of primes in G to primes in G mod n in this quotient. Okay, I have to get some exceptional set here. And the exceptional set I'm going to write down is at first going to look kind of bad. It's going to look sort of very similar to sort of the kinds of exceptional sets from Peirce, Turnage, Butterbaugh, and Wood, and from Thorner and Zaman. It's going to sort of consider kind of this intersection problem, except that it's a little bit tweaked. What this is looking at is it's trying to say how often do you have these fields that intersect, but not sort of at this normal subgroup we're kind of bypassing. And this is actually useful because, for example, if you consider your Galois group to be Sn and your normal subgroup to be An, so okay, you're in this situation where we're kind of getting rid of the quadratic subfield. Well, actually, An is the only interesting normal subgroup of Sn. And so if you're bypassing it, you're kind of bypassing everything. And if these two fields do not intersect sort of at this normal subgroup, then they actually have to intersect sort of everywhere, and they have to be the same. And this kind of weird intersection multiplicity is just 1 in this case. So it's actually very easy to understand. And so this is going to be kind of a key point. Okay. So again, on the next slide, I'm going to kind of process this sort of main term a little bit, kind of tell you how I think about it. But just kind of as a key sort of thing to say, there's actually sort of content in something that's sort of not written in this theorem. In particular, this theorem does not assume the Artin conjecture. And so if you were to take sort of the zero density estimate we're ultimately going to prove, that I'm going to mention to you sort of later on in this talk in kind of part 2, then it would be sort of relatively straightforward if you assume the Artin conjecture to obtain the conclusion of this theorem. And so actually a key step in our argument is to kind of prove an approximate Artin conjecture in this world that lets us kind of bypass the need to do that. Okay. So let's process the main term. Let's figure out what this theorem is kind of actually saying. And I'm going to do this in kind of my favorite example in this world, which is this world here, where we're sort of considering Sn relative to An. And so I'm just kind of phrasing sort of this theorem in exactly that world, that if you have x bigger than this sort of large power of the log discriminant, we're able to get something like this, okay, for all but O of q to the epsilon Sn extensions. And so we've shifted the burden from understanding sort of this Chebotarev problem in this Sn extension into understanding it and now this quadratic extension. And so this quadratic extension, again, you should believe there's some kind of Chebotarev theorem there. And if you have that, I would tell you that primes are just sort of evenly split between the two conjugacy classes and sort of in this much smaller Galois group. But okay, we're bypassing the subfield problem by sacrificing the information it tells us. Our theorem has no ability to tell you anything about what's going on with this prime counting function. And so you have to allow for the possibility that these primes can kind of be distributed however they are. In this particular, kind of write this in this form, where depending on the sign of your permutation C and Sn, you're going to get sort of a corresponding boost or sort of deficit in the distribution of such primes. Okay. And so what I want to do is just kind of give an example of kind of what that actually means in practice. So I'm just going to write down the densities of these primes inside S5 for various values of delta. So you can see the effect of sort of this delta on the overall distribution of primes kind of upstairs in this Sn extension. So the first world to consider is just delta being equal to 0. This is the perfect Chebotarev world where everything is distributed exactly like you want it to be. But our theorem doesn't tell you that you get the perfect Chebotarev world. And in fact, if you want to apply our theorem, you almost have to imagine that your worst enemy is choosing this delta. Your worst enemy is choosing sort of how the primes are distributed downstairs. And if they wanted, instead of choosing delta to be 0, they could have chosen delta to be 1, which will kind of zero out all of the odd conjugacy classes. Or they could have chosen delta to be -1, which will zero out all of the even conjugacy classes. So that sounds quite bad, because if you look at this, it means in particular that they can kind of choose this delta to kill whichever single conjugacy class you care about. But the content of this theorem is that if they're doing that, they have to be doing it in a very, very specific way. And it's possible to look at this sort of overall kind of picture of this full distribution of these densities and extract a lot of information. So if you want to understand just a single conjugacy class, our theorem is not going to help you. But if you want something that's kind of can be understood, kind of fiber by fiber, can be understood sort of over each possible sort of case of what's going on down here, then you're actually in very good shape to be able to apply this theorem. Just as an example of something you can extract from this, kind of regardless of what this delta is here, okay? So be it sort of one of these numbers or sort of something in between, and actually regardless of what n is as well, kind of in the Sn up here, one thing you might extract from this is the average number of fixed points of, and that turns out to be exactly equal to 1, regardless of what delta is, regardless of what n is. And this is something that is very nicely connected to the splitting behavior of prime ideals. So a consequence of this theorem is that Jesse and I actually get a very strong, effective prime ideal theorem for almost all fields, sort of in, for example, this Sn family. And so that would look like something like the following. If you start with an Sn extension, you take a subfield of it that misses this kind of excluded sort of problematic quadratic subfield. Okay? Then if you look at the number of primes that are degree 1, okay, in F, where x now is sort of bigger than, again, sort of the same sort of log power type range, you get exactly the right number. This is a problem that can kind of be understood fiber by fiber. You can piece these fibers together. You can get a very strong result on the number of primes inside sort of these subfields of Sn extensions that miss this quadratic field. And this is applications. In particular, it has applications to things like bounding class groups. And an example of this is provided by a lemma of Ellenberg and Venkatesh. And what it considers is the l-torsion subgroup of these kinds of fields F. So bounding the l-torsion subgroup is actually a very hard problem. And sort of the best we can do sort of in general, typically, is to bound it sort of trivially by the size of the class group, which is going to be bounded by discriminant to the 1/2 plus epsilon. Okay? More on that actually in a couple of slides. But we sort of have this kind of trivial bound the l-torsion. What this lemma of Ellenberg and Venkatesh lets us do is, if we understand prime ideals that are very small and are split in this field F, we're going to be able to get some savings. And so, loosely speaking, this is what their theorem says. It says you sort of get an improvement over the trivial bound based on the number of small primes you're able to find, where small means sort of bounded by this power of the discriminant. Well, this sort of bound on sort of the size of the discriminant, this is way too small for something like the Lagarias and Odlyzko style sort of Chebotarev theorem to tell you anything about. But it's actually perfect for something like this sort of effective prime ideal theorem that Jesse and I prove. So as a consequence, we're able to show that, for example, for any n greater than 3, and all but sort of a teeny exceptional set, O of x to the epsilon sort of degree n extensions that have total Galois group Sn, you're able to get this sort of kind of bound on the size of the l-torsion subgroup of the class group. And so just some kind of remarks. So again, this improves on the trivial bound, okay, just coming from bounding the class group as a whole. Okay. In the case of small degrees, sort of for n up to 5, here we actually understand how to count fields. And sort of using different techniques and actually using field counting techniques, Ellenberg, Pearce, and Wood obtained kind of a similar style result, sort of the same bound on the l-torsion subgroup of the class group, but for a much larger exceptional set of fields. Pearce, Turner, Chebotarev, and Wood, sort of one of the main applications they had in mind for their kind of effective Chebotarev density theorem was to bound on l-torsion subgroups of class groups. And kind of as a consequence, for n greater than 6, if you're willing to assume the Artin conjecture and the discriminant multiplicity conjecture, you can get kind of the same sort of style thing. Thorner and Zaman, sort of again, sort of under now, I guess, the intersection multiplicity conjecture, are again able to get something. But in both of these cases, kind of with large exceptional sets, because fields genuinely do intersect. And you sort of have this subfield problem that is structural and baked into these problems. Okay. Another application that we like quite a lot also concerns bounding class groups, but kind of from the other direction. So in particular, we can consider the extreme order of class numbers. What is the biggest possible class number you can see? And there's a theorem that follows from work of Riemann and from work of Duke, that if you look at a totally real degree n extension that has no subfields, so for example, a degree n Sn extension has no subfields, so we're just sort of looking at totally real degree n extensions with no subfields, then if you're willing to assume the generalized Riemann hypothesis, you can put an upper bound on the size of the class group in this form, where it's discriminant to the 1/2 times the power of log log divided by power of log. So the way this works is Riemann gives a lower bound on the regulator of number fields depending on their subfield structure. That'll kind of give you this denominator. And Duke shows that if you assume GRH, you get an upper bound on the residue of the Dedekind zeta function, essentially of this form. So you kind of plug it into the class number formula, and this pops out. Okay, maybe you don't like this because maybe you're not an analytic number theorist, and you're not a huge fan of these log logs to a power. But unfortunately for you, Jesse and I show that this is essentially the right answer for how big class numbers can be. We show that for any degree n, there are infinitely many totally real fields with no subfields, for which the class number actually is this size. So this, I should say, sort of improves on work of Duke, who obtained the same conclusion under the assumption of GRH and the Artin conjecture. Work of Peter Cho, who removed the need for the generalized Riemann hypothesis, but still needed the assumption of the Artin conjecture. So in particular, Cho's work actually applies in degrees up to 4, unconditionally. There's also work of Flamenco, who gets a worse lower bound than this, unconditionally. Littlewood, who proves this for n equals 2, and work of Ryan Dilita, who proves this unconditionally also for n equals 3. But in particular for large degrees n, this is, I think, new. All right. So there are other applications I could tell you about, but I think this is a good time to pause for questions and sort of then kind of transition into talking about how one actually goes about proving effective Chebotarev theorems.
So the only question in the chat up to this point is asking for your slides at some point.
Yeah, I think that should be no problem. I want the ability to sort of check them for typos sort of one last time, especially after giving a talk where you inevitably find 5 typos. But yeah, I'm definitely happy to post those. Okay.
Oh, so there's one question just popped up. Can you say a bit more about where the delta comes from?
Sure. So let's see. So that would be, I guess, sort of the delta is, I think, this delta. And essentially sort of what this is basically saying is it's just kind of a parameter that controls sort of how far off from equidistribution primes in this quadratic subfield that we're kind of discarding the information about sort of are like kind of it's telling us kind of about that discrepancy. And so what we're actually sort of sacrificing by dodging problematic subfields is a full Chebotarev theorem would not have sort of this quadratic sort of kind of sub-Chebotarev problem kind of there. This would just be about pi of x. And so it's kind of saying, well, if we understand the distribution of primes in this quadratic field, then we understand the full thing. So that's kind of what we're sort of sacrificing sort of by dodging this subfield problem. There are definitely some other natural n and g to consider. So kind of a nice thing that happens about Sn is because it has a unique minimal normal subgroup. This is actually true for S4 as well, just kind of with the Klein 4 subgroup. That sort of this intersection multiplicity that we need, Jesse and I need to consider, kind of this this kind of MGN, that's going to be 1 whenever you have this unique minimal normal subgroup. So Sn kind of an An is a very nice example of this. There are lots of other things you could look at. For example, you could look at kind of dihedral groups of order 2p, or more general semi-direct products of the form like Z mod p cross some subgroup of aught Z mod p, I think you can probably do Reith products. There are lots of things where you have this kind of minimal normal subgroup for which you just sort of have no worries whatsoever about how to understand kind of this sort of normal subgroup kind of intersection multiplicity kind of thing. Let's see. All right. So I'm not seeing any more questions popping up in the chat. So let's transition now to kind of part 2 in talking about how one goes about proving an effective Chebotarev density theorem. And I'm going to take a kind of slightly idiosyncratic perspective on this that is going to pay dividends kind of at the end when we want to talk about this kind of Chebotarev density theorem for fibers, where we really are kind of going for a holistic view of sort of the distribution of primes, not the distribution of primes in a single conjugacy class. And so the way I'm going to approach this is by sort of taking advantage of the character theory of finite groups. So here's just like a one-slide crash course in what I need to know about character theory of finite groups. So if you look at the space of class functions on the group, these are functions that sort of go from your group to the complex numbers that are invariant under conjugacy. So you sort of plug in 2 conjugate elements, they sort of, the outputs are going to be the same. Well, it turns out this thing forms a complex vector space on which there's a natural inner product given sort of by this expression, which I actually sort of like to think about sort of in the following terms. Where I want to sort of think about this kind of function, or each function, as being just sort of the list of the values kind of for each sort of element of the group. And then what this inner product is doing is it's basically just taking the dot product of these 2 lists of numbers kind of tabulated, I guess, horizontally, the way I'm sort of setting this up. So you have this inner product on the space of class functions. And a very nice thing is true here, which is that there's a very nice orthonormal basis for the space of class functions given by the characters, which is sort of the synonym for traces in this context, of irreducible complex representations of our group G. Okay, so if you've not seen this before, I think it's good to see an example. So if we look at kind of the simplest non-abelian group, S3, you have 3 irreducible representations here, corresponding to the fact that actually there are 3 conjugacy classes in S3. So there are kind of the dimension of this space is 3. And these 3 irreducible representations, well, 2 of them are pretty easy to come up with. You're going to have the trivial character that sends every element just to 1. You can have the sign character that sends a permutation to its sign plus or minus 1. And you get one sort of more interesting one, which is the trace of a 2-dimensional representation given sort of in this form. So I'm telling you kind of the value on just a transposition. Here's a value on a particular 3 cycle. We want to extract from this the trace. So the trace of a transposition under this representation is just 0, and a trace of a 3 cycle under this representation is -1. Okay. So with this like one-slide crash course in character theory, what I want to do now is actually just consider an example of sort of an effective Chebotarev kind of problem. So in particular, I want to look at the first 6001 primes and see how they split in sort of this field here, which is an S3 extension. Okay. So I'm saying 6001 here because this field is ramified only at 31. And so if I do this, I'm getting 6,000 unramified primes. That's kind of a nice number with respect to the size of the group, which is 6. So in particular, I can just tabulate the number of primes in each conjugacy class, sort of in this Galois extension. We see sort of numbers like this. And then the next thing I want to do is going to be a super artificial step. Okay? There's not sort of a whole lot of arithmetic meaning in what I'm about to do, but I'm about to take this number 3002. I'm going to split it up equally between these 3 elements of the conjugacy class. I'm about to take this number 2012 and split it up between these 2 elements of its conjugacy class. Okay? I'm going to do that. I'm going to call the resulting object sort of capital pi k of x0. Okay? So it's kind of like a prime tabulating class function. Okay? This is sort of associating to each element of the group a number that has something to do with the distribution of primes. And so apart from sort of making this a class function, one other very nice thing that pops out from this is that it makes it really, really clear the kind of thing I'm trying to prove if I'm trying to prove a Chebotarev density theorem. Namely, I'm trying to prove that all of these numbers I've listed are basically the same, I'm trying to prove that all these numbers are about 1,000. All right. So if I do regard this pi k x0 as a class function, that then means I can bring in the characters that I sort of developed on the previous slide to bear. So I'm just listing their values here. And then basically everything I want to do can be very nicely interpreted in terms of these irreducible characters. Particularly my target, this thing that I'm trying to prove is all sort of 1000s. That is actually just sort of the orthogonal projection of this pi k of x0 onto the trivial character. It's basically saying make everything sort of as equal as possible, okay, from sort of our initial sort of prime data. But if you remember a little bit of linear algebra, you remember that these characters form an orthonormal basis, then I can just find sort of this projection by starting with pi k x0 and subtracting off its contribution from these other two irreducible characters. So I have sort of the sign character, I have this trace of this two-dimensional representation. But these are things I can just compute by taking these kind of weird dot product. And the output of that is just going to be these two numbers, minus 2/3, or I guess 2/3, and 20/3. Okay, so what is kind of the key point here? The key point is that these two numbers, 2/3 and 20/3, understand absolutely everything about the distribution of these 6,000 primes sort of in this extension. And the other thing to observe is that these two numbers are actually really pretty small compared to the number of primes we started with. In fact, we started with 6,000 primes, we ended up with 2/3 and 20/3. That feels like we're doing something. And so this is the strategy we kind of want to adopt going forward. Okay, so the point is that if we can show that these two numbers are small, kind of for a general value of x, not necessarily this one where I've just computed these things, we've just like done it by hand, then that's going to show that this prime counting class function is very close to sort of its orthogonal projection onto here. It's very close to kind of making everything just equal by fiat. And that is exactly what we need to do to prove a Chebotarev density theorem. Okay, so how do we do this more generally? Well, for a general K, maybe an S3 extension, maybe some more complicated thing, we can form exactly this kind of prime counting class function. That's a sort of weird thing, but this knows everything about the distribution of primes in this extension. And for each non-trivial irreducible representation of our group, we can consider the inner product of this kind of weird class function with that trace of that representation. And our goal is to show that each of these things is small, so that sort of our function is very close to being equally distributed. And actually, if you sort of think about what this sort of weird inner product is, sort of this kind of dot product-y type thing, it actually turns out if you just kind of plug it in, what you actually just get out of this is that it's the sum over primes up to x of the trace of Frobenius sort of with respect to this irreducible representation. And this should make you happy. This is the kind of thing that is controlled by explicit formulas for L functions, and in particular is controlled by the Artin L function attached to this representation. So it'd be defined like this. Okay, and so you might sort of think, okay, let me just go to like Avanians and Kowalski, look up what's known about Artin L functions. I'll just be able to kind of get a Chebotarev theorem from that. There's a problem. And the problem is that these Artin L functions are not in general known to be nice L functions. So what is known? So it follows from work of Artin and Brouwer that sort of each LS row is meromorphic and has a functional equation of the type you sort of would expect. So it's very nearly an L function, except that there's one operative word here that you don't usually see, namely the word meromorphic. Okay, so it's actually sort of a conjecture of Artin, this is the Artin conjecture, that each of these LS rows is actually entire. We don't know that. But if we assume the Artin conjecture for a second, then if we sort of go to Avanians and Kowalski, sort of use like kind of that axiomatic framework, I would be able to say, well, we have a zero free region for this L function. Then the explicit formula kicks in. Okay, that'll tell us that sort of this inner product is small. And that sort of is what we need to get Chebotarev. And the mantra you want to have in mind is that if you have a better zero-free region, this gives you a better bound sort of on this inner product. You get a better effective Chebotarev density theorem. Okay, but how do we actually go about getting the zero-free region? And what if we don't want to assume the Artin conjecture? So there's a very nice workaround that kind of follows from work of Artin and Brouwer. Okay. And so there's this lemma of Artin that basically says that for any sort of Artin L function you might look at, okay, I have no idea sort of if this thing is holomorphic or not, but I can at least express it in terms of things I do understand. So in particular, you can express it as a product over characters chi, sort of L functions of the form ls chi, where these are characters of cyclic subgroups of your group. And these exponents, c chi, are rational numbers. So this at least sort of puts it on some analytic footing. And there's a lemma of Brouwer. Okay. Or sorry, I should say that, yeah, these characters of cyclic subgroups, kind of Artin reciprocity, says that these things are Hecke L functions, and so entire. And so these are sort of nice L functions. And then there's a lemma of Brouwer that basically says that if you have a zero-free region for this quotient of zeta functions, then that actually sort of has to transfer over to each of these ls chi's. So these things are then going to be entire, sort of in this region omega, and they're also going to be non-vanishing in that region. So that means that kind of regardless of what these rational number powers are, be they sort of things like 1/3, be they negative numbers, you're not introducing any sort of actual problems into this Artin L function. So the upshot is that if you have sort of this non-vanishing region for this quotient of zeta functions, then your Artin L function is well behaved in that region as well. Okay. So kind of the strategy for an effective Chebotarev density theorem then is to get a good zero-free region for this zeta function. And this standard zero-free region is due to Stark and also sort of Lagarias and Odlyzko, and it essentially asserts something of the following shape. You sort of have at most 1, 0 in this kind of region that kind of gets really, really close to the 1 line as s goes off to infinity. And if you take this standard zero-free region, okay, and you plug it into the machinery I was talking about sort of on the previous slides, I claim, maybe sort of no surprise given the names I've attached to this, you'll end up with the Lagarias and Odlyzko effective Chebotarev density theorem. This is very much not the language in which they talk about things, but I claim it's kind of morally equivalent to what they're doing. Okay. But the sort of Lagarias and Odlyzko style effective Chebotarev density theorem was not enough for the applications we had in mind. And so we need to get a stronger Chebotarev density theorem. That means we need a stronger zero-free region. And that's actually a really hard problem. Sort of to do that for a single k is quite difficult. And so this is sort of the idea of Peirce, Turner, Butterbaugh, and Wood, is it to bring in sort of these so-called zero density estimates. And so they're kind of the basic scheme of a zero density estimate, is that you have some family of L functions, and you want to show that something kind of like GRH is nearly true for almost all fields in your family. Well, what I want to do is for each of these sort of L functions in my family, just count the number of zeros in this sort of box here. And if I do that, the basic sort of output of a zero density estimate is going to be sort of an estimate of this form that basically says that the total number of zeros for any L function in my family can be bounded by something of this shape. And the way this should be processed, if you haven't seen this kind of thing before, is that, for example, I can take, so maybe my t to be the size of my family, I could take sigma to be 1 minus 1/4c. These are our numbers rigged, so the kind of the output here is going to be size of L to the 1/2. If you do that, you can then say, okay, how many L functions in my family have a 0 in this region? Okay. Well, however, may be bounded above by the total number of zeros across sort of any sort of element of your family in that region. And that's this kind of thing that this thing can handle. We get sort of out from this sort of a kind of square root type estimate. And so what that would mean is that basically sort of at most sort of kind of square root of L, many L functions in your family have a problematic 0. Okay, this is actually sort of a very clumsy sort of set of choices to be taking sort of in a zero density estimate. Okay. You make much better choices that kind of are more suited to the problem at hand. Okay. You can conclude that basically all but a really small exceptional set of L functions in your family do much better than sort of the standard zero free region. So this is kind of the basic structure of a zero density estimate. And sort of a fundamental zero density estimate one might want to work with is one from Kowalski-Michel, which basically gives a general zero density estimate when you have a family of irreducible automorphic L functions. And so the basic tack okay, but I guess like I should say, there's a problem here though, which is that if you want to apply this to Dedekind zeta functions, two things can arise. The first problem is that sort of this density estimate applies to irreducible automorphic L functions, and the Dedekind zeta function isn't irreducible. It can be factored in terms of these Artin L functions. And the other problem is that we sort of don't know that these Artin L functions are known to be automorphic. And this is essentially the content of the Artin conjecture. It's the strong Artin conjecture. So the basic tack adopted by Peirce, Turnage, Butterbaugh, and Wood is that if we're willing to assume the Artin conjecture, then we can apply this zero density estimate of Kowalski and Michel, and then use the discriminant multiplicity conjecture to control sort of the subfields, which are going to correspond to factors here that appear for many different fields in our family. So kind of control the propagation of zeros using this discriminant multiplicity conjecture. And kind of the idea of Thorner and Zaman is to prove a zero density estimate kind of directly for sort of this quotient of zeta functions. And this kind of carries with it a natural factor of this intersection multiplicity. Okay, so the starting point for my work with Jesse is the observation that this kind of technology used to prove this kind of zero density estimate directly transfers to another kind of quotient. Particularly if you look at the family of L functions that come about from taking a quotient of zeta k divided by sort of this kind of problematic subfield we're trying to exclude, then we're able to get a zero density estimate for this family that looks like the following thing. All right, so you sort of fundamentally, kind of the mechanics of this are very, very similar to the work of Thorner and Zaman, but sort of you need to be a little bit careful in how you set it up, and you need to do a little bit of extra work. Okay? But kind of at core, this is sort of the Thorner-Zaman style zero density estimate. It's not actually obvious what this tells us. Particularly sort of the entire approach to sort of this effective Chebotarev density theorem that comes about sort of kind of from the previous slides is that you can transfer a zero density estimate for zeta k to the Artin L functions and then understand these inner products. Well, if we're willing to assume the Artin conjecture, it's pretty clear what this should tell us. Turns out you can factor sort of this quotient in terms of Artin L functions, whose kernel does not contain this normal subgroup n. And if you, again, assume the Artin conjecture, then a zero free region here is going to transfer to a zero free region for each of these Artin L functions. And then that sort of says, well, okay, so now suppose I've got this good zero free region. What does that actually tell me about arithmetic? Well, what it tells me is that sort of, again, by using this kind of explicit formula style thing, that this inner product of this kind of weird prime counting class function against sort of these representations is going to be small. And so I think this is sort of made most clear by way of example, where we come back to our favorite example, which is with Sn and An. And what this looks like in this case, well, this An is not contained in the kernel of any irreducible representation of this group, except for the trivial representation and the sign representation. So in other words, kind of these are the only two actually sort of unfaithful representations of Sn, kind of are just these two. And as a result, if we go to our prime counting function, we might sort of break it up in terms of the irreducible representations. And if I look at this, then these inner products are controlled by kind of this first line up top. We can assume these inner products are small, which is basically saying that these representations are pretty much not showing up in the decomposition of this prime counting class function. And so you're just left with sort of the understanding of the trivial character and this sign character. And this should seem a little bit weird, but if you start thinking about it, well, I sort of don't immediately know what this inner product is, This thing is the thing I would sort of get if I had sort of true Chebotarev. I'm sort of happy with that term. What this is basically doing is it's sort of saying, well, according to kind of the sign of the class you're looking at, kind of correspondingly sort of like boost or decrease kind of the counts of the primes. And that should sound kind of familiar. Right? This sort of kind of weird sort of inner product, I claim has actually sort of appeared earlier on in this talk. It's sort of this delta times pi x over g, just kind of some normalizing factors, where delta is exactly the delta that's controlling the distribution of primes in this quadratic subfield. Okay. So this is essentially sort of the strategy for Sn. This sort of works sort of the more general setup, assuming the Artin conjecture. So I see that I'm basically out of time, but let me just sort of state that essentially sort of one of the main results we prove and kind of one of the main techniques we develop is a way to kind of get around sort of the need to assume the Artin conjecture in this problem, which would just kind of amount to the following kind of result. That basically you have a zero-free region for this quotient, then it transfers over to sort of these Artin L functions you might want to use. And let's say that this is sort of very much not something that follows directly from work of Artin and Brouwer. You really do have to kind of get your hands dirty and prove this. But I think I should probably stop in the interest of time and ask if there are any questions. Thank you, Mackenzie. As I'm waiting for questions, I might sort of idly sort of flip through the clicks. There's a diagram I spent a long time sort of putting up in TIC-Z that I sort of wouldn't mind just kind of flashing on the screen.
That's an impressive TIC diagram. Wow. Okay, we have one question. So if you were able to prove a log-free density, density estimates, how would that modify your number of exceptions?
So that's a reasonable question. I think sort of the ultimate answer is that it wouldn't make a substantial difference. Sort of in that sort of the way we're applying things, I think you'd sort of end up getting still some sort of small power of exceptions. But I'd have to kind of think a little bit and kind of don't want to sort of answer that definitively on the spot. But my initial reaction is that it probably wouldn't be a substantial impact. Let's see. I see another question in the chat about whether our methods give bounds on the first sign change of the coefficients of the representations. So certainly sort of what I'll say is like kind of in concert with sort of the zero density estimate we prove, kind of this sort of transfer of zero free region absolutely lets us prove things like a prime number theorem for these Artin L functions in kind of this very small range, kind of from the earlier parts of this talk. And so kind of from that, sure, you'd definitely be able to get something just kind of by exploiting cancellation in that representation. Whether we're able to do anything more sophisticated, I'm not sure.